Imagine watching a pendulum swing its motion governed by unseen forces. In this lesson, we'll uncover how gravity pulls, tension balances, and energy transforms to reveal the elegant physics of simple harmonic motion. A pendulum consists of a mass, called the bob, suspended from a fixed point by a string. When displaced from its resting position, gravity pulls the bob toward equilibrium. The restoring force is proportional to the sine of the displacement angle. Because the string exerts no torque, the motion remains confined to a plane. The bob's kinetic energy increases as it swings downward and decreases when moving upward. At the lowest point, all potential energy has converted to kinetic energy. When the bob reaches its maximum angle, velocity drops to zero and potential energy peaks. The time taken for a complete oscillation is called the period. For small angles, the period depends only on the string length and gravitational acceleration. This relationship allows pendulums to serve as precise timekeepers in clocks. Pause 0.8. When a pendulum swings, the bob moves along an arc defined by its string. Gravity pulls the bob directly downward toward the Earth's center at all times. At any point on the swing, gravity can be split into two parts, one along the string and one perpendicular to it. The component of gravity that points straight down is counteracted by tension in the string, keeping the bob from falling away. The remaining component of gravity, which lies horizontally toward the lowest point, acts as the restoring force that pulls the bob back. Because this horizontal pull changes direction as the bob moves, it creates a continuous cycle of acceleration and deceleration. Tension in the string is always directed along the string toward the pivot, balancing the perpendicular weight component at every instant. The net force on the bob is there for the horizontal component of gravity alone, which points toward the equilibrium position. This net force produces a torque that causes angular acceleration, driving the pendulum's oscillatory motion. In a vector diagram, you see three arrows: gravity downward, tension along the string upward, and the horizontal component pointing to the center. The interplay of these forces explains why the pendulum swings back and forth instead of simply falling straight down. Thus, gravity provides the restoring force, while tension balances the perpendicular weight, allowing smooth periodic motion. Pause 0.8. A pendulum swings like a clock hand, its bob moving up and down. At the highest point, all motion stops momentarily. Kinetic energy is zero. The bob's height gives it maximum potential energy, stored as gravitational work. As gravity pulls the bob downward, potential energy converts into kinetic energy. Speed increases while height decreases, showing a clear exchange between energies. When the bob passes the lowest point, speed peaks and kinetic energy is at its maximum. Immediately after, gravity slows the bob upward, turning kinetic back into potential. This cycle repeats endlessly in an ideal frictionless system, conserving total mechanical energy. The graph overlay shows height on the vertical axis and speed on the horizontal, color-coded. Red lines trace kinetic peaks, blue lines mark potential highs, illustrating conservation visually. Pause 0.8. First, we write the torque about the pivot as I umlaut equals mgl, sin I circumflex. Newton's second law for rotation gives I circumflex plus or minus equals I umlaut, where I is the moment of inertia. For a point mass at distance L, I equals mla circumflex 2. Substituting gives mla circumflex 2I circumflex plus or minus equals mgl sin I circumflex. Divide both sides by ml to get I circumflex plus or minus equals g/L sin I circumflex. Now we use the smaller euros angle approximation, sin I circumflex is circumflex letter 2 c6 I circumflex, when I circumflex is measured in radians. The equation simplifies to I circumflex plus or minus equals g/L I circumflex. Recognizing that angular acceleration I circumflex plus or minus is the second derivative of I circumflex with respect to time gives dA circumflex 2I circumflex / dTA circumflex 2 equals g/Li circumflex. This is the standard simply a euros harmonic differential equation, whose solution is I circumflex t equals I circumflex s circumflex euros cos I umlaut t. The angular frequency I umlaut equals sqrtg/L. Finally, the period t is related to I umlaut by t equals 2 I umlaut euro/I umlaut, giving t equals 2 I umlaut euros a circumflex letter to C6s hatchek L/G. Pause 0.8. The small angle approximation replaces the sign of an angle with the angle itself, when that angle is measured in radians. This works because the Taylor series for sin theta begins as theta minus theta 3/6 plus higher order terms. When theta is less than about 0.1 rad, the cubic term contributes only a few percent error. In practice, we consider angles up to roughly 15 degrees acceptable for most pendulum calculations. The approximation turns the nonlinear differential equation into a linear one that can be solved exactly. Consequently, the period of a simple pendulum becomes independent of amplitude in this regime. The plot below overlays sin theta and theta across 0 to 30 degrees, shading where their difference exceeds 5%. Notice how the curves coincide almost perfectly up to about 10 degrees, then diverge slowly. This visual cue helps students see why the approximation is justified for small swings. By simplifying the dynamics, we can focus on the underlying mechanism of harmonic motion without algebraic clutter. Pause 0.8. First, imagine a perfect pendulum swinging without any resistance. Its amplitude stays constant because no energy is lost to the surroundings. Now add a small air drag that exerts a force opposite to the motion. This drag removes kinetic energy each time the bob passes through the lowest point. Consequently, the amplitude decreases gradually with every swing. The period also changes slightly, because the restoring torque is now balanced by resisting torque. Friction at the pivot adds another source of energy loss, further speeding up the decay. In practice, we observe a damped oscillation that eventually settles at rest. Mathematically, this behavior is described by an exponential decay factor in the amplitude term. Thus, real-world pendulums provide a clear illustration of how non-ideal forces modify motion. Students often model this by adding a damping coefficient to the equation. When plotted, the envelope of the swings follows an exponential curve. Pause 0.8. First, gather a sturdy string about 50 centimeters long. Attach one end securely to a fixed point above the pendulum's center of mass. At the other end, tie a small dense weight, such as a metal ball. Make sure the string is taut and free from knots that could alter tension. Next, use a ruler to measure the exact length from pivot to the center of the weight. Mark this distance on the string with a small flag for reference during timing. Set up a stopwatch or smartphone timer beside the pendulum, ready to record swings. Pull the pendulum gently to an angle of about 15 degrees and release it without pushing. Count 10 full oscillations while the timer runs, then stop and note the elapsed time. Divide the total seconds by 10 to obtain the period. Compare this value with the theoretical formula T equals 2 I umlaut euros a circumflex letter 2 C6s hatchek L/G. Pause 0.8. We explored how gravity and tension drive pendulum swings, how energy shifts between potential and kinetic forms while conserving total mechanical energy, and derived the simply a euros period formula under small a euros angle assumptions.